So thanks Adam for joining us, and thanks for supporting this webinar today. Also, I think that Deeplearning4j is our flagship project in terms of artificial intelligence at the Eclipse Foundation for the moment. And I must say that we really appreciated what you said on Twitter when you decided to bring the project. Like we decided to go to Eclipse because that's the perfect mix between business-friendly open source and community-driven open source. So maybe I summarize that that's really cool, and thanks for that. And yeah, the floor is yours.
Okay, so I asked kind of what the mix of the audience would be, given that it's a lot of people interested in AI or AI practitioners. It's a little Eclipse biased, so given the prominence of Jakarta EE, so I'll describe it. I'll describe some of the associated concepts briefly, but try to keep it more associated with people who might know Python or data science, like the more mainstream AI folks. So this talk's going to cover how to run. It's going to be more focused on deploying AI instead of how to build models and things of that nature. So it'll be fairly high level. Anyone who has at least interacted with an IDE, the Eclipse one, for example, should be able to understand most of my talk here. So I'll just cover a little bit about DL4j. So DL4j is actually, I created DL4j 7 years ago now. So it's been a long time. Most of my 20s went to creating it, and now we have a decently sized team. We punch well above our weight. In the time that DL4j's existed, I wrote an O'Reilly book. I've built a remote team, and we've seen DL4j used by more than half of the Fortune 500. So something not well known that we're working on improving is that DL4j in a lot of contexts is typically used by software teams, even by companies that have their own deep learning frameworks. Typically there's different business units within companies, and some of them, actually many of them, will co-deploy DL4j or a component of it alongside what you hear about with TensorFlow and PyTorch. But when I built DL4j, it was never meant to be the de facto research deep learning framework. You had Theano and Lua and Torch for that back then. It was always aimed towards enterprise, which is why I chose the Eclipse Foundation in the first place. And since then, we've kind of, we've focused a lot more on lower level concepts, in C++, just like everybody else does. But, we still have kind of the existing large Java user base. So we work, something not well known is we work within the Keras community as well. And we also participate in TensorFlow Java as well. So TensorFlow Java's underlying packaging actually relies on our open source technology as well. So we work heavily within the open source community and within different standards. So if anyone has questions just about the broader machine learning framework community, I know every single framework, and I'm happy to discuss anything about the ecosystem or just anything. I always get the Python versus Java question. If you want to ask that, you can. But beyond that, I will continue here. For those that don't know, I'm talking to you from Tokyo. Despite being an American, I've lived here 5 years. Hopefully that covers it. So where is DL4j used? Well, our biggest user bases are in China, America, and Germany. That's where we see most of our traffic. We got our start building. Our main niche we've noticed in server deployments is NLP workloads. So NLP is text analytics, sentiment analysis, chatbots, things like that. Another niche we've noticed is something people don't know is we can actually directly import the Keras and TensorFlow file formats as well. So if you write a Keras model and you save the model, we can load it. The same for TensorFlow as well. So we have our own parallel implementation of the concepts in TensorFlow. there's this concept of an operation like 2 + 2, like an addition operation. There's, God, I think at least 1,000 operations, if not more, in TensorFlow now. We support importing more than half of them. So we can run, and I think we're 99% compliant with Keras, both 1 and 2. So the old file format as well. So DL4j's focus is more on deployment, as I mentioned, and helping enterprise developers run AI workloads, whether it be on Android, which we see decent market share in, or in IoT use cases as well with the Raspberry Pi. So this focus will be more on the mainstream Java audience with Jakarta EE. So if you've ever used Spring, if you've ever used Tomcat, you've probably used Jakarta EE technologies underneath, the specifications. Servlets and all that are all based on specs hosted at the Eclipse Foundation. This is a brief overview of what we kind of see today. When you want to deploy AI, whether it be TensorFlow or PyTorch, you have one team that knows this framework and they know Python. You have another team that uses another open source project built, single vendor open source project, in this case TF Serving or TorchServe, recently announced by Amazon, to run models for a specific framework. Turns out a lot of people have existing IT investments, and so what they'll do is they'll instead turn to our model import and run it on their existing infrastructure. So we see this pattern a lot in banking, automobiles, you name it. A lot of existing technology tends to use Tomcat among other web application servers. So right now the default mode is basically put a blob of C++ that you don't really know what's going on in a Docker container, and then you run it. So the way DL4j views frameworks is they're a file format we implement and run in production. So we're more focused. I believe Mindspore has a broader focus and can cover a lot of the concepts being done in TensorFlow and PyTorch. Hopefully that frames the two frameworks when we have discussions later. So as I mentioned, the typical Java ML use cases, like where is it widely used? Manufacturing, telecom, financial services. DL4j itself serves millions of users. We're everything from Apache Spark deployments to existing IoT gateways as well. We see it's all over the place. I mean, the Eclipse IoT working group is all about Java stuff. So a significant amount of the Java middleware is written, or IoT middleware is written in Java. So we aim to integrate with, we aim to solve kind of the integration problem. Since we're written in Java as well, it's very easy for us to work on embedded devices or just big clusters. Doesn't matter. We've seen everything. So Jakarta EE. So what are the problems? So Java developers typically when they write code will target Java application containers. The problem with that is everything is shared resources, shared connections. That used to be a good thing. You used to have a big platform, but the problem with that is you don't have isolation. So for those of you who don't know Java very well, Java has this concept of a class loader, which means an individual file. And in Java, a compiled source file is a class. And so the class loader also takes care of resources. So if you want to use a Java native interface, there's a lot of problems with that. Java native interface is the interface between Java developers and low-level C++ code. So DL4j is actually mainly C++. But the bulk of our developers are actually written in C++, targeting all the major compilers and things like that, just like every other framework does. But our Python is Java. So the easy to use interface, the focus, the deployment is all Java. What a lot of people may not know, they just use the framework, but if you actually dissect it, for example, TensorFlow, 1/4 of it is written in Python. So there's a lot of things, a lot of extensions, easy to use application code. There's very much a Python focus. which is okay because most of the AI development does happen in Python. But when you want to run things with your existing IT infrastructure, sometimes that may involve Java. Hence the problem we're trying to solve by providing the same primitives, you know, and hardware acceleration that you would normally see, that you would normally not see in the JVM. You know, so we're aiming, you know, so we solve a very specific problem. We handle memory allocation ourselves. So we actually have our own, we actually do our own memory allocation. We do not rely on Java's GC, actually. All of our allocations happen off heap. So what does that mean? There's a concept in a garbage collected language. You have a heap, which is basically managed memory, but then there's off heap. So if your programming language gives people access to C or native code, then you can allocate memory within those within that native code that you're accessing. It's generally called an FFI, a foreign function interface. So what will happen is, you know, every programming language is typically written in C or C++. That's what most of them are written in. And then you have a compiler, and then it runs native code, assembly, whatever. So Java itself is heavily written in C++. Python is written in C. So that's why you have access to all these low-level concepts. So these concepts are exposed in the higher level language. And so getting back to where I was with off-heap memory, that memory is allocated by the low-level underlying C runtime. So most Python code is actually an interface to low-level code written in C. And so all those hardware optimizations and things like that, you don't have to use Python technically. It's just what people use because it's easy to use and it has traction. But in general, all that stuff is actually implemented by compilers written by the major hardware vendors. You know, for example, Huawei will present later, they have their own chip and everything, and they have their own instruction set compiler SDK. So a lot of, this is what a lot of vendors will do. They'll optimize popular interfaces but change the underlying infrastructure. So we do something similar, but targeting Java developers or you know, enterprise developers. So you have a Python framework, it saves something written in a file format, we load it. This is true for many of the frameworks. And so one of those low-level concepts in math is called OpenMP. It's an open spec for basically allowing a compiler to say, I'm going to run vector compute. So vector compute is used in cameras. It's used in rendering your laptop, you know, the screen on your laptop. It's used in video games. It's used in machine learning. So this has been a concept that's been around a long time. So Java and math can work, but they don't implement a lot of the processor-specific instructions because Java is a cross-platform language. So there's only so much. There's always going to be limitations in what you can do when interacting with things from Java. So our approach is to solve that for the user. You know, so we give you we know how to combine large enterprise on-prem enterprise deployments, the JVM, and low-level concepts like off-heap memory and math code. So we can recommend to you, how do I run a distributed, how do I do distributed training? We can tell you how to spec that. How do I do inference, where inference is the idea that you use an AI model. So you input some data like a picture and you get out cat or dog. That's called inference. So how do you do that reliably and in a performant fashion? We can tell you how to do that, and we work on the low-level optimizations to allow you to do that while still giving you something easy to use. So there's a lot of, so as I mentioned though, because we do that, there's actually a lot of problems with the traditional model of using AI within large Java Jakarta EE servers. And so the way we solve that is something called Java CPP. It's not an Eclipse project, but it is heavily used within the ecosystem by a few different projects of the Apache Foundation, DL4j, as well as you know, the Rapids project from NVIDIA. Google's TensorFlow also uses it, and we basically handle packaging of all the low-level libraries that you would normally only get access to from Python or C in Java. So we can provide MKL, we can provide cuDNN, we can provide CUDA, we can provide anything that you would normally need to install. We can provide that as is, and it's going to be optimized and put in a jar file. That jar file is going to be large, but it's there and it's optimized for specific hardware. So we handle the whole end-to-end approach ourselves, and that includes being able to do our own memory allocation and everything. We actually have the concept of a pointer. So when we write, when we write Java code, we typically write it like C or C++. We do that for you though. You don't have to. We have access to all the same optimizations, but none of the but you more or less don't need to know this exists. This just allows us to, you know, prepackaged binaries, you know, for like AVX12 optimized math or all the other floating point buzzwords you've heard of if you know, if you're familiar with benchmarking different kinds of processors. So you know, so what we focus on is MicroProfile. So MicroProfile is an attempt to, in a set of specs, vendor neutral specs, for taking the existing Jakarta EE and shrinking it down to a simple runtime focused on microservices instead. So a lot of developers, I believe, are familiar with that concept by now. The idea with microservices is that you can write things in multiple languages. It's easier to support, and instead you focus on scaling. Obviously, microservices do have a lot of problems, many, including observability, ease of maintenance, and sometimes I don't even recommend using microservices, especially depending on the concept of the complexity of your application. But generally, you know, teams know how to cope with these things by now, and so MicroProfile kind of rose up as a way of shrinking down the spec and making and reflecting more modern software development practices. So what we do is we solve the problem. You know, we previously solved the problems of running things in low-level servlet containers, and now we also support people running things on MicroProfile, you know, with simple microservices. So where do we come in? You know, the class loader issue I mentioned earlier is solved, and that allows easier management of native libraries. You know, again in Java CPP, we did technically solve the concept of loading, you know, duplicate native libraries and sharing and things like that. We did solve that, but you know, just to make it less error prone for other libraries, if you're integrating them, you know, we suggest you know, pushing microservices because it has better isolation. It allows you, you know, for AI especially, it allows you, you know, you can have a specific server, say with a GPU or a more specialized processor, to handle the AI workloads. And that way you can deploy more commodity hardware for most of your applications, but then build the AI workloads in a self-contained environment. So what I'll do is I'll just go through a quick use case example. So this is the MNIST data set. So if you write data science code by now, you're probably facepalming at this example. Again, this was more targeted to general audience, so I apologize to those of you in advance if you know this well. I expected most people will. It's mainly meant to be a relatable toy example. So the idea of the application is that you upload a file and you get a classification back. So the file in this case is just literally a file upload on a form. So depending on your technical expertise, you know, if you've done some web development, you know what a file upload form is. You hit submit, you upload an image, and you get back a result. So what in this case it's identifying which digit it is. Fairly simple to test, fairly easy to show. And the great thing is what I'm going to show here is a vendor neutral implementation. So these are more MicroProfile specific concepts, but basically you have in MicroProfile, the idea is that you have a runtime that looks at the annotations in your Java code and understands what do I need to do here? What do I need to load? What do I need to handle for the user? What is the user requesting? So if you want to request resources for your application, the runtime gives it to you. And so that's the idea with a MicroProfile. You have multiple vendors that implement a web application runtime, and then it loads your code, and then it looks at your annotations, and it shows the behavior you're intending your code to have. So in this case, we have you know, if you're not familiar with the MVC architecture, I won't go into it too much, but basically, if you are, you know what a service is. And in there, we have two things. We have two concepts to focus on. An image loader, this is all backed by OpenCV. If you're familiar with that, we develop so at Java CPP, we also develop a project called Java CV, which is basically an interface for Java for OpenCV as well. And yes, OpenCV has their own, but we have our own that integrates with several other libraries, and typically has been used as a viable alternative. For those of you that use OpenCV might be confused why we have our own bindings. There's your answer. So the other concept is a simple multi-layer network. So in Keras, if you're familiar with Keras, this would be a sequential model. So it's just a simple, straightforward input-output network that classifies digits. So we load that network and we declare it as a resource. And then what we do is we have, this concept of a singleton. So I'm just going to zoom in on that real quick. A singleton says only load one copy of this, never more. So if you're familiar, so after the application started and created, what we do is we load a model. So again, very simple. We load the model, and in there we have, we have a one-liner that, in this case, we have an input stream. If you're technical, then you generally deal with byte streams. So if you're not, sorry, this is a technical talk, but happy to answer questions offline. So anyway, so you load an input stream, and then you have something that loads an image. In this case, like as you know with MNIST, it's 28 by 28, so 28 pixels. So rows and columns, and then one channel. So if you're not familiar with images, they generally have, if they're color, they generally have 3 channels, RG and B. But when you have black and white, you typically only do 1 channel. And so what we do is after the application's created, we load the network, and then we load in this case, this is our data pipeline. So in machine learning, you need to take your plain input data, an image or text, and you convert it into a mathematical representation. You then use that representation to run, to get a result out. So that is what this image loader is doing. After that, when you want to actually predict something, what you can do is you just convert. We just do this conversion as I mentioned. This is a raw image, so this is an input stream. It loads the image. You get the input. You run the multilayer network and get the output, and then you get a result out. So this is math that basically says create an array of the labels. So if you have more than one image or what have you, then this will output more than one. But in this case, it's just one result. So what we're going to do is say we send 2 in, this output will be 2. That's essentially all you need to do in this case. And what we're doing is we're converting probability. So when a neural network outputs a classification, almost always what it is it outputs a probability. Like it's 20% likely that it's 0. It's 0.1% likely it's 2. It's 90% likely it's 10. That's what it will do in this context. And then we use something called CDI, so basically dependency injection. So the idea is that you have the server-side code where the end user uploads the file and then it sends it off, and then it sends it off to the service. That's the controller. So again, if you know MVC, you know what a controller is. Basically, it's just the thing that the user interacts with that invokes a specific action. And in this case, what we're doing is we're per request. We're using this model service right here. So the container, the runtime, the Jakarta EE runtime knew to create this and put it in and to put it in this controller. And then this is for processing file upload. So as I mentioned, it's all HTTP. So all we do is we get the part out. So if you're familiar with multi-part uploads, you get the part. There's only one part. It's just the image. You run the prediction, and then you return the response. So most inference works like this. So if you're not familiar with machine learning, essentially, again, it's just input data, output result. Most, or I would say many binary, like images or media that you send to machine learning, typically is a lot of it's file uploads. So you'll input a result, you'll input data, you'll get out a result. There's generally a data pipeline. So this model service just encapsulates the concept of load image, run math code, get back out result. So most, or I would say many you use machine learning every day. When you do, you're basically using code like this. So when you click a button, chances are it looks like this. So hopefully this demystifies machine learning for those of you who aren't sure what it is. Hopefully this demystifies it a little bit. It's just input data, get output result. Generally, it's done over HTTP. And it's done with concepts that most people actually have dealt with in some form before. So that was the end of the talk. I'm happy to answer questions after or during the panel or whatever.
Yeah.
So thank you.